Okay, let's continue our lectures. And now our subject is chaotic representation or random variables, which are measured with respect to Gaussian generalized random element in the separate ring Hilbert space. Let me recall what we did last time. So we considered Hilbert space H, which is real and separate, and consider here generalized Gaussian random element with zero mean, like we wrote, and covariance of xi is equal to identity of grade. Of course, we know that there are no such random element in this space. In case when dimension h is equal to plus infinity. So psi was constructed as follows. Let us consider a sequence psi n, which are ID and standard normal values. Then consider En orthogonal basis in H. Then one can define psi as a formal series. This is a sum from n equal 1 to infinity psi n. We discussed that such series does not converge because of the sum of squares is equal to infinity with probability 1. But despite of this, one can define for any element of H the scalar product H psi, which is equal as usual to the sum from n equal 1 to infinity. HK psi. And this sum is well defined. It is Gaussian random variable with known parameters. H psi is Gaussian with the parameters 0 and norm of H square. So we, instead of random element itself, we have a set of its products with the elements of the space H belong to. And it is evident that these random variables are linear with respect to first argument. And from this relation, it is very easy to get that the product of H1 psi H2 psi has expectation which is equal exactly H1 H2. This reflects our idea that psi must have identity covariance operator. This set of random variables leads to other name of psi. It is often called by the Gaussian white noise in the Hilbert space H. When we will consider examples, we will see why this name arises. Our aim is following. Since psi is infinitely dimensional generalization of the standard Gaussian vector, one can expect that if we have a square degree random variable which is measured with respect to psi, it must have a Hautic representation which is similar to the finite dimensional case which we discussed before. So our aim is to find for a random variable which is measured with respect to psi and square integrate representation like following. Here is sum from n equal to 0 to infinity, an from psi, psi. We already have such representation in the case when H is finite dimensional, and we know that here an is symmetric and linear form, and this symbol denotes some special construction involving Hermite polynomials from the coordinates of psi. So how we plan to get the same representation in the infinitely dimensional case? Our idea was following. Let us consider sigma field Fn, which is generated by the n first coordinates of our generalized random element. Then it is evident that sigma psi is the smallest sigma field which contains the union of these sigma fields Fn, and which is important, that Fn is increasing family. I will write it non-formally. Fn increases to sigma psi. Exactly under this condition, one can recall the Levy theorem, which says that such conditional expectation of alpha with respect to Fn converge in N2. It converges in different senses because it is martingale and closed martingale now, but we need in N2 and n tends to infinity. And our idea was following. Since alpha conditionally with respect to Fn depend only on a finite number of coordinates, psi1, psi_n, it already has Hautic representation. And after this, we want to go to the limit. Today, we will do exactly that. So, let me for a moment denote alpha n. This is not power. Maybe I will need these indices. Let me think. Okay, maybe it is enough to use it here. Then I can say that alpha n is the representation sum p equals 0 infinity a n psi x. Here a n is asymmetric. Is symmetric linear form. We can say for the first 10 coordinates, but I prefer to say it as follows: on Hn, which is equal linear span of the first n elements of basis. Okay, then what we already said, that alpha n tends to alpha equals x. But first of all, let us calculate the distance between alpha n for different indices. So now I'm supposing that n is greater than n, and we consider alpha n, which has exactly similar chaotic representation. And let me note the following interesting fact, that alpha n can be considered as an element of L2, sigma, here we have notation, Fn, Fm. Since then, it must have chaotic representation, which is using the first m psi 1 and so on, psi n elements of our sequence psi. Since then, I can, since then, and due to uniqueness of chaotic representation, I can say that this K-linear symmetric form are defined on the HM, not HN. Due to this, I can consider simultaneously to this chaotic representation and check the distance, L2 distance between alpha n and alpha m using the distances between these forms. We will get the following formula, which is the one of the property of this, such representations. Expectation of alpha n minus alpha m square is equal to the sum from n equals 0 to infinity and factorial multiply on the norm a k, oh excuse me, n is not appropriate index, k equals 0 k factorial a k n minus a k m square, and I must put here index k. We already use it, which says that we use here Hilbert-Schmidt norm in the space of k-linear form, but also I will use here symbol n, which emphasizes that we have two symmetric k-linear forms on the space HM. We have such equality, and from the last one, we can use the representation of this form in the along the basis E1, E2, and so on infinity. So I will write this more explicitly. It will look like this. K factorial. Here is one sum. E1 ek equal 1 to m. Here is a n k, then E1 k minus a m k E1 e k square. That's all. I will not write. These are coordinates of this form in the basis E1, En. So we have such relation, and we know that the left hand side of this relation goes to 0 when n and m goes to infinity. What does it mean for our coefficients? It means that for any fixed number of the coefficients, we have the limit. Moreover, it means much more interesting. Unfortunately, I have to erase this. It means the following, that there exist the numbers A1, Ek, which are symmetric, and such that symmetric with respect to permutations of indexes, such that the sum from E1, Ek, 1 to infinity, A1 Ek square is less than infinity, And the limits of our sequences. I will write it precisely, but let me know that from this relation and the properties that they are symmetric, one can say that these coefficients can be considered as a coordinates of AK, which is equal to the sum from 1 ek equal 1 to infinity, a1 ek here e. And this from this relation, one can see that AK is a k-linear symmetric Hilbert-Schmidt form on the space now on the whole infinitely dimensional space H. So I will say that
sorry, could you please clarify how this AK is related to our AKN and AKM?
I will write this.
Okay.
Just wait a second. It is evident that this is a limit of the coefficients. Yeah. For fixed.
Okay, so these A's are limits of coefficient of differences of coefficients. Yes.
No, by differences. We know that this one.
Okay.
Tends to 0, yes?
Why?
Because the sum square tends to 0. We already have, let me recall it, that we have the relationship that expectation of alpha n minus alpha n square tends to 0. Yes?
So why we have this? I said that we were going to show this.
No. It follows from the Lewis theorem. We have
okay, thanks.
To alpha.
Okay, thank you.
Then this is fundamental, and this is fundamental, so we have the limits. We have one can define such AK, which belongs to denote H K symmetric. So this is K-linear symmetric Hilbert-Schmidt form on our space H. And moreover, now we know that A Kn minus AK, here is now only K because this is infinitely dimensional already case, tends to 0 when n tends to. Okay, now let us associate with AK some random value. Let me denote. Let me introduce this random variable. It's easy. This is a sum from E1 ek equal 1 to infinity. K E1 ek. Here is psi E1, psi ek. We already use this notation, and it means weak product. More precisely, it can happen that between the indices, one can find equal. So we just collect equal indices, organize power of corresponding random variables, and then substitute this power by the Hermite polynomial of the same degree. The simple example is following: xi1 multiply xi2 multiply again xi1, for example, is equal to h2 of xi1 multiplied by xi2. So usually product will be xi1 square multiplied by xi2, but instead of square, we use the Hermite polynomial of the second degree. So we have the following series, and it's easy to check that the series converge. And we will denote it, excuse me, we will denote it as before, AK psi. Here we have such kind of random variables, and now, of course, one can expect that our random variable alpha will have exactly the representation as the following: alpha equals the sum from k equal 0 to infinity ak psi. Series will converge again because the limit exists, and so there are a few very little technical moments in order to check this, which we need to check this equality, and leave it to you as an exercise. It's easy. So from one side, we get our aim because obtained representation has the desired property. This is generalized Hermite polynomial of degree A. The summands are orthogonal because the prelimit summands were orthogonal. And we prove that now expectation of alpha, of course, is equal A0. Just number. Expectation of alpha square, again, because this is a limit, is equal to the sum from k equals 0 to infinity k factorial ak k square. So now let us think, is it unique or not? And maybe it is not hard to check that it is unique, because we mentioned that this is a closure of polynomials of degree exactly k. So if we consider the all polynomials sorry. If you consider all polynomials from the infinite sequence psi n, then again this set can be orthogonalized, and one can consider the following. Let E K with eta is a2 closure of all polynomials of degree non-greater than k. Why we need now this procedure? Because we have infinite sequence, and when we consider only polynomials, then, for example, this okay, this is a polynomial, and this is a polynomial of degree 1. But if we want to consider its limit on the n capital tends to infinity, which exists, and is also Gaussian random variable, jointly Gaussian with psi n. It's natural to say that this is also a polynomial of degree 1 from our sequence, but not in algebraic sense. So I just say that this is too closure. Then again, we discussed this before, that now all L2 L2 sigma psi is just P with tilde, closure of all polynomials. Yeah, it follows from the same fact in finite dimensional case and VVC remedy. And now that we introduce these subspaces k indicated by n, which is defined as the orthogonal difference by p n minus p n minus 1. K0 is just equal to r, so constant. And then one can easily check now that this is the orthogonal sum. Orthogonal sum from n equal 0 infinity of our k. And now, what is the summands in the chaotic expansion of random variables alpha? If alpha is sum of n equals 0 to infinity, n psi and then n psi is just a projection. Pn of alpha, where Pn is a projection In such a way, we understand that this summand is unique, and we want to say that the corresponding random variable can be put into correspondence with one Hilbert-Schmidt form on AN. To understand this, we again need random variables which are very familiar to us, which has already very good chaotic representation, and which we use to define, to find coefficients of chaotic representation for any other random variables. These are stochastic exponents. So to understand invariance of this an xi with respect to different bases, let us consider stochastic exponents and chaotic expansion for them. So if H is element of our Hilbert space, let us define corresponding stochastic exponent H as follows. It is equal exponent H xi minus 1/2 of norm of H squared. Then let us find the corresponding chaotic expansion. One can use a one-dimensional case. Yeah? One can use one-dimensional case. Suppose that norm of H for simplicity I denoted by lambda. Then H is equal lambda on H1, where norm of H1 is equal to 1. Then I can rewrite this. E of H will be equal to E lambda H1 xi minus 1/2 of lambda square. And now you recognize the generated function of Hermite polynomials. So I can say it's equal to sum of n equals 0 to infinity. Here is lambda power n, divided by n factorial, and Hermite polynomial of degree n from H1 psi. Now let's look precisely on this expression, namely, let me consider the following Hilbert-Schmidt form, very simple on H. This will be H1, H1 exactly 10 times. And it's easy to see that it is symmetric And of course, Hilbert-Schmidt, because it's one-dimensional, so it belongs to H or N symmetric part. So if I consider H1 from side, by definition, it will be exactly Hermite polynomial of order n, of degree n, from H1 xi. Due to this, one can rewrite the chaotic expansion for our stochastic exponent as follows. H is equal to sum from n equals 0 to infinity, lambda and factorial. Here is H1, H1 times here is x. But now lambda was defined as the norm of H. So what happened if we multiply lambda on this tensor product, lambda in n power? We get exactly lambda in n power multiply H1 is exactly H. So finally, our stochastic exponent is equal to sum from n equals 0 to infinity, 1 over n factorial, and here is H of xi. Now let's consider together with this the chaotic expansion for arbitrary square degree random variable. Here is an xi, and just as we did before in one-dimensional, finite-dimensional cases, take the condition, the expectation of the product, then we will get that expectation of alpha stochastic exponent of H is equal to sum from n equals 0 to infinity. And factorial will be cancelled because of the formula for expectation. And what we have, when we have here the product of in the space of symmetric and linear form, and H just H N and of course it is equal sum from n equals 0 to infinity, and here is an from H. That's the result, because now we understand that this function is analytic with respect to H. This is power series. And now we understand that its coefficients, these forms an, are uniquely defined by this function. So it is useful for us in order to understand, by the way, this as a chaotic expansion is invariant with respect to choice of the basis, and if we introduce Fourier unit transform of alpha, we still will call this as a Fourier unit transform. Then how an can be found? We just take the nth derivative when h equal to 0 is equal to n factorial multiplied by n. So we have such a relation. Of course, in this vector derivative, we have to understand that we differentiate the function of the Hilbert valued argument. So the first derivative is element of Hilbert space, the second derivative is the element of operators on bilinear forms on Hilbert space, and so on. So this n-linear form, and we get it as a derivative of Fourier transform. So this is one way how one can get the elements of chaotic expansion for arbitrary random variable. Now it is easy to understand that we have a way to define stochastic derivative and the adjoint operator using this chaotic expansion. So let me show you the definitions. So I will say that alpha is stochastically differentiate if there exists random element d alpha which belongs to space of square integrate random element, usually it's denoted by omega ph. So it is a random element in the space H, but it is integrate with respect its log in square is integrate with respect to measure Q. Such that for arbitrary H belonging to our space, dH multiply d alpha multiplied by H is scalar product is equal to the sum from n equals 0 to infinity, and here is an H psi here is n minus 1. So what happens there? When you substitute instead the first coordinate the element h, we obtain from n-symmetric Hilbert-Schmidt form n minus 1 symmetric Hilbert-Schmidt form, and after this we substitute the psi via procedure as we discussed before. So this definition of stochastic derivative, and one can check against this closed linear operator, and as before, the set of all stochastically differential random variables I already known by W1. And now one can say again that this the set of stochastically differential random variables W1 is dense in the set of all random variables. It's easy to see because the finite sum of finite elements has stochastic derivative. So then one can define a Joule operator. E is equal to D with star is correctly defined, and even one can easily understand how it looks like. Why? Because E must act from the space which we already introduced of the square integrate random elements into the space of random variables. Then we have to know how the transform of the random elements from here looks like. It's easy. If we have some x which belong to omega pH, then if I take,
I'm sorry. I'm sorry. What is the sigma algebra in the space L2 omega pH?
the same sigma
The same.
psi.
So the difference is only that
This is
the
just,
values in H or in R.
yes, this is just a matter of notation. It, by the way, this notation came from quantum physics, and if you check such a nice book, Richtmeier, Principle of Mathematical Physics, Richtmeier, then you will find a lot of interesting things about such space and related space, about the continuum integral of Hilbert spaces and so on, and you will see the same notation. Okay, so if we have the random element from there, then this is element from there, because it has square integrated bound, so it must have Hermite expansion to infinity. Here is what H n, but it depends on H and x. And now, because of this square integrability, one can easily check that this Hn is actually n plus 1 Hilbert-Schmidt form. So it belongs Hn plus 1. But of course, it is not symmetric with respect to all its coordinates. There are no reasons for this. So now, how looks like the action of the adjoint operator? It occurs, and it is a good exercise to check this, that Ex is equal to sum from n equals 0 infinity lambda an psi. But let me recall you that here we have n plus 1. So we have this one. Then we build symmetrization lambda n, which belong already symmetric part. N plus 1 symmetric. And here we have such representation. Of course, it can be checked that it doesn't converge for any random element. But we didn't expect this because we know that stochastic derivative is unbounded operator, and it's natural to expect that joint also will be unbounded operator. And we will see that it is true even in one-dimensional case. So we have such a definition, such nice representation. We will call it as I announced before, E is extended or Skorochod. Integral of x. So we now are at the following stage. We introduced chaotic expansion and main stochastic operators for functionals from the generalized Gaussian element or Gaussian white noise in infinitely dimensional Hilbert space. Separate Hilbert space. Now it's time to use the tools which we get, because at least 2 last lectures can seem very formal, and now it's time to introduce the examples and to use obtained machinery. We will do this during the second part of our semester. Today, this is end of the lecture. Thank you for attention. Maybe somebody have questions or comments, please. Okay, if not, then thank you again, and see you next week.
Thank you.
Bye.
Bye.
Bye.